Hello, this is Claire and we're going to talk about Pythagorean triples. Now, we've talked a little bit about this before and we know that a triple, like 3, 4 and 5, is a very well-known Pythagorean triple and they fit exactly into a right-angled triangle. So 3 units on the base and 4 units on the other short side, and 5 units will form 5 units on the hypotenuse. And because those are whole numbers, we call them Pythagorean triples. We've also seen that if we multiply each of these by a scale factor, we form an infinite number of other triples. So if we double each of these, it would be 6, 8 and 10, we'd form another perfect triple. And if we multiplied each by 3, so 9, 12 and 15, we'd get another perfect triple. In fact, you can get an infinite number of triples just by multiplying each of the numbers by the same scale factor. But there are other methods of getting triples because there's other patterns with the digits that can be used to form right-angled triangles, and there is a little formula that you can use. So I'd like you to draw a table, please, and I'd like you to experiment with this. So firstly, we'll call the first digit we use n. So make a column and call that first column n. That's going to be the first digit we use. Then we'll use the next digit. We're going to call that m. So I'll give you a little bit of room. And we'll call that digit m. So we'll start off with 2 digits. M must be larger than n. So let's start off with 1 and 2. To form the side length A on our Pythagorean triple, so we know that we call them, say, A, B and C or A, B and H, A is formed by squaring m and subtracting the square of n. So m is formed in that way. So I might just write that above there. So A equals m squared minus n squared. So that's my first column, how to find A. So make your next column A equals m squared minus n squared. Our next length we're going to find in our Pythagorean triple is B. B is formed by multiplying n and m together and then doubling them. So it's going to be 2 times m times n. And the last digit in our triple is found by squaring m, we'll call that c, m squared plus n squared. And that looks very much a bit similar to the Pythagorean theorem, doesn't it? So we've made a table up and we're going to experiment with a few numbers. Now the one rule is that m must be larger than n because otherwise you're not going to be able to do this subtraction. So the first value of A that we're going to find, let's write A, B and C very large above those columns. So A is going to be m squared minus n squared. So that's going to be 2 squared, which is 4, minus 1 squared, which is 1. So that's going to be 3. A is 3. So we're going to actually get this triple here, but it's a good place to start. So B is going to be 2 times n times m. So 1 times 2 is 2, times 2 is 4. And now we're going to add the squares of these. So 1 squared is 1 and 2 squared is 4, so we get 5. Can you see we've generated that very first triple that we already know about? That's great. It's just verified that method. Let's try the next two numbers. Let's make n 2 this time and make m 3. Let's see what triple we get. So, squaring the m, which is 9, 3 times 3 is 9, minus 2 times 2 is 4, we get 5. Now multiplying these together, 2 times 3 is 6, times 2 is 12. And the next one, we're going to actually add the squares. So it's going to be 9 plus 4, which equals 13. I wonder if that is a perfect Pythagorean triple. You can test it by using the Pythagorean formula. So we could add another column here for testing and checking. So the way we would test them is we would have to say, does a squared plus b squared equals c squared? So that's what we're required to prove there. So we would say, does 5 squared plus 12 squared equal 13 squared? So that will be 25 plus 144. And that would equal 169, which is 13 squared. So let's have a look at it. Turn your calculator on. And we will go 25 plus 144 does in fact equal 169. And if we find the square root of 169, we hope to get 13. So use the square root button, 169, find the square root, and it is 13. So we've just verified that. So we've found a brand new triple, and that triple there is not formed by a multiple of that 3, 4, 5. So it's a brand new relationship. It's a brand new unique triple. So let's try another one. So we'll have 3 and 4. So again, m does need to be larger than n. So let's square this second number, 16 minus 9. So 16 minus 9 is 7. There's our first side length. Now multiply these together. 3 times 4 is 12, times 2 is 24. There's another triple. And now you're going to add these two numbers together. 16 plus 9 is 25. What's a brand new set of numbers? 7, 24 and 25. Let's test it. So 7 squared plus 24 squared. If we add those together and find the square root of it, will we get 25? So 25, remember, squared is 625. So that's what we're hoping to get. So 7 squared is 49. What's 24 squared? Clear the calculator. So 24 squared, because 576 plus 7 squared, which is 49, is 625. Well, we already know that the square root of 625 is indeed 25. So that is verified. So we know that that definitely gives us another triple. The next triple we're going to use will make n the next chronological number, which is 4, and we'll make this larger as 5. So 5 squared is 25, 4 squared is 16. So if we add 9 to 16, we get 25. So the next thing is 4 times 5 times 2. So 4 times 5 is 20, times 2 equals 40. Now we need to add these numbers together. 25 plus 16. So that's going to equal 41. So I wonder if these numbers form a perfect triple. Just to double check, we need to actually test them. So 9 squared plus 40 squared. So we hope that when we get this, the answer will give us, when we find the square root of the answer, we'll get 41. So let's work this out. 9 squared is 81. So turn our calculator on. 40 squared is 1,600 plus 81. And now we'll find the square root of 1,681. So square root 1,681 square root, you get 41. So we've been able to verify that. Can you find some more Pythagorean triples using this algebraic method? See if you can. See if you can find 10 brand new triples. We've already found 1, 2, 3, 4. See if you can find another 6. Bye for now.